nanoHUB.org. Online simulation and more for nanotechnology.
Now, entering our problem, going back to our challenge, that was reproducing the blue morpho butterfly optical effect. We will consider this paper as our main reference. The researchers here developed a structure on a quartz substrate to mimic the effect of the blue morpho butterfly. Remember, we talked about a Christmas tree-like structure. So here the researchers built a structure that looks like this. We have multiple trees arranged periodically in this direction, while they have infinite extension in the other direction. So our problem here is 1D for S4. Ultimately, you would like to reproduce the same shape of the tree here for each unit cell. However, for simplification, we will consider to have a unit cell that looks like this, actually multi-layers of alternating layers of PMMA and air in between, and a support of another material called LOR. And you will find the definition of all the geometric parameters like the period and the width of the plates and like the support lengths over as you go in the upward from the substrate. All will be found in the provided reference here. But for us, we would like first to start with a simpler problem. We will not build that structure directly. We will start easily and take it easily. We will just benchmark what we've learned before. We've learned about the problem of a normal incidence at a semi-infinite plane that we called medium 2, remember in the a couple of slides before. And we would like to benchmark this problem with the simulation tool. So we would like to solve for the reflection coefficient at the interface between air and the quartz substrate and find the reflection coefficient for normal incidence, that is n1 minus n2 over n1 plus n2 all squared. We call this relation Fresnel equation for normal incidence. Okay? And when we, after we benchmark this problem, we get the solution for a refractive semi-infinite plane, we can go further and build upon the substrate. We can build simple multi-layer structure like this, that look like this in this paper, to mimic the effect of the blue morpho butterfly. So we will make a structure that is similar to the tree, but with some minor modification, dropping the change over the space when you go up, just making a multi-layer structure with a support with the same length in between. That could be a simpler structure to start with, and we can solve for the reflection coefficient and get the results. And compare them to the results in the paper. Once we do that, we can start to add more details to our tree structure, reduce the widths as you go up, reduce the width of the support, increase the number of layers, play around with the materials, and so on and so forth. You can do any kind of modification and tuning, so you can tune the effect to give you the reflection of the blue morpho butterfly or a similar effect. After we get the results, we need to conclude something from our results. We need to read the reflection coefficient to know what it tells, maybe think more about what parameters can help us control the wavelength of reflection, or even what happens when you have an incidence that is off the normal incidence, maybe with an incident angle of 30 degrees or 45 degrees or something like that. So, in fact, the fabricated structure in the paper will look something like this. And the measurements and the simulation results of the fabricated structure shows us a good match between what the researchers expected from the simulation tool, and this is actually a great example to show us the power of simulation, that the simulation will help us foresee the upcoming results of the actual experiments after fabricating the actual structure. So you see here, it has infinite extension this direction. You have the tree structure, tree-like structures here. They experimented with the dimensions, what happens if we fill in between the layers with the LOR material. We can do that in simulation. We will do it in our tasks in the simulation. But looking at the results here, what we would like to see is something like this, the reflectivity function and against the wavelength. And here, the simulation results plotted in black shows us a peak here between 450 and 500 nanometers. Whereas for the real wing scale, if you take the actual butterfly and measure the reflection from it, you will see also a similar peak for the blue curve here from the actual wing, which tells us that simulation results are actually very close to the actual wing scale of the blue morpho butterfly. You can vary all the way. You can, change the dimensions. Blue 1, blue 2, blue 3 are different structures that they have tried in their experiment and in their simulation. You could see the differences between the places of the peak. Here produced maybe a greener peak. This is a baseline reflection reproduced by maybe this structure. You can see similar results in the paper as well, and hopefully you can reproduce some of these results in your requirements and maybe innovate more to create different effects and to play around with the reflectivity function as well as the angular dependence. With that, I would like to thank you all and conclude this presentation. We have discussed the blue morpho butterfly as an example of structural coloring that gives effect of magnificent colors, although it is not pigmented with that color. We studied the wing scale of the blue morpho butterfly, which inspired artificial structures with added tunability and selectivity, and this actually have numerous effects in providing lenses that are flat, in creating different optical materials, cameras, compact devices, and so on. And we've shown here the power of electromagnetic simulation in understanding, analyzing, and tuning many of the optical effects in nanostructures nowadays. Thank you all for listening to this presentation. I hope you will enjoy your simulation. And at the end, I would like to thank Tanya and Joe and all the nanoHUB team for giving me this opportunity and for providing very helpful and useful feedback preparing this material. And finally, I want you to have fun. This is the important thing. Thank you very much.